Hey everybody, this is going to be our lightning fast quick review of functions. I'm going to move fast, so if you have some questions about this, take notes, hit pause, rewind, listen to it again, do whatever you need to do to make sure that you have all this information, because I'm going to move kind of quick. To begin with, a relation. A relation is when we have two sets of numbers. Then those sets are going to be big X and big Y. That's containing all the X values and all the Y values. So we're saying little x is a member of the big X, so each individual value we're going to, in the set of X, we're going to call little x. Each individual value of the set of Y we're going to call little y, and these make up our coordinate points. So a relation is a set of coordinate points. Okay? Functions are relations, but they're a special piece in there. No individual x can have a different y. So for example, if you had two coordinate points, the first point being 1, 3, and the second point being 1, 7, that is not a function because an x cannot have a different y. Y's can have different x's, but x's can't have different y's. So to say that again, if we had 1, 3 as one of our coordinates, and then we had 2, 3 as our second coordinate, that's okay because y's can have different x's, but no x can have different y's. We'll talk about that a little bit more as we move on. Within our functions, independent variables are always going to be the x's. That is something like time, things that you cannot control. Those are going to be what our independent variables are. And just as with that being our independent, our dependent variables are going to be the y values of a function. Okay, so everything that happens with the x is going to have a reaction, or is something that's going to be depending on that, that's going to be your y value. Okay, domains. The domain is every value in the x function, or every value of x in the function. So that would be the set of x's like we talked about in our relation. And the range is going to be all of the values of the y in a function. So if we pull out all the x's, we pull out all the y's from our coordinate points, that would be our domain and our range. An image is the y value that specifically corresponds to each individual x value. So like I was saying, 1, if you have coordinate 1, 3, the image of 1 will be 3. So the y value that coordinates to that 1 is 3. So that's what your image is. Our notations, we're used to seeing equations written like this, or maybe like this. Our functions are written a little differently. They've got this funky thing out here. And that reads as f of x, or the function of x. All you really need to remember is that this is the same thing as y. So when we're talking about f of x, we're saying y. Okay, so those two are the same thing. And the reason we do that is because as mathematicians, we tend to sometimes be kind of lazy and we want to make things a little bit easier for ourselves. So we could say instead, what is f of 3 instead of, so here we would say f of 3 instead of going up here, what is the value of y that corresponds to x when x equals 3? That's a mouthful. We don't want to have to say that every time we're trying to work out a problem. So we say, what is f of 3? And speaking of which, let's take a look. What is f of 3 for this function? How would we do that? What does that look like? All we're doing is, here we see f of x, and we're going to replace all of our x's with 3. So here we go. Here's our equation again. We take x, we replace it with 3. We take x, we replace it with 3. We work it out, and f of 3 is 9. So now we have our coordinate, the x value being 3, the y value being 9. So that's how we solve a function for a specific value. Moving on, let's look at some examples of domain. So we've got two different functions here. We've got g of x and f of x. Both look very, very similar, but there is a difference between the two. The domain for g of x is going to be x such that x does not equal 2 or negative 2. Now, why would I say that it doesn't equal 2 or negative 2? If we plugged in 2 here, 2 squared is going to be 4. 4 minus 4 is 0. You can't have a function where you are dividing by 0. That's undefined. Same thing happens when you have a -2. So if you have -2 squared, you're going to have 0 in the denominator once you work that out. That's undefined. So this is going to be all real numbers except for 2 and -2. This one is a little different. It still follows the same rules that it couldn't be 2 or -2. However, within the function, it defines what the domain is. It's going to be every single number between 4 and 5. All of the decimals, all the fractions, everything in between there, including 4 and 5. So the domain here is going to be everything between 4 and 5. So when it's not stated, you have to think about all the possibilities. When the domain is stated, then you just you already have it there for you. So what is the domain and range of this function? We've got the square root of x minus 1. All right, well, we can see that, again, we've got some kind of issue inside here. What can x not be? Well, x can be everything. It's not going to be any negative numbers because we're not talking about imaginary numbers right now. So our domain is going to be that everything is bigger than or equal to 1. And it's going to go on infinitely that way. And we can write it this way, saying x such that x is greater than or equal to 1. Or we could write it shorthand in a short way with this bracket and this parenthesis. This means equals to, so it's including 1. And this means it's going all the way up to infinity. So that's another way to write what the domain is. You can write it either this way or that way. What about the range? Let's take a look at the graph. Where are all of the y values going? Well, here again, we're also not going into anything smaller or any negative numbers. So our range is going to be y such that y is greater than or equal to 0. Or you could write it again in interval notation, square bracket 0, comma, infinity, parentheses. So we're not including infinity because you can't ever get to infinity. So that's why it's an open or a rounded bracket there. Okay, moving on. What about the domain and range of this function? The famous tangent function, everybody's favorite. Well, first we have to think about what these blue lines mean. These things are asymptotes, right? So asymptotes mean that the function never actually gets to that point. It keeps on going and going and going, but it never reaches that point. So we have to consider the domain in between each one of these. And if you remember, our asymptotes fall for our standard tangent function. They fall right on pi over 2. So our domain is going to be all x's excluding pi over 2, 3 pi over 2, 5 pi over 2. So you keep on adding some constant to your pi. So you're going to just keep on repeating that, and it's going to go in both directions. What about our range? Well, our range is going to keep on going infinitely up and infinitely down. So that means our range is going to be all real numbers. We're going to account for all numbers in that function. All right, last one. Domain and range for this function. Wow, this is a weird looking one. This is called a piecewise function. This is saying that when x is less than 1, we're going to do this function, this equation. This function. When x is greater than or equal to 1, we're going to do this equation, square root of x minus 1. So let's take a look at what this graph looks like before we do anything. So we're going to graph this thing. We see we're going to have this straight line because this is a linear equation right here. So we've got this straight line going off here with our negative slope. And then as we saw in the previous function, we've got the square root of x minus 1. It's kind of this rounded up going off this way infinitely. So what is our domain? Well, there's kind of a hint right here. It's saying that x is going to be less than 1, and then x is going to be greater than or equal to 1. So that kind of tells us it's going to be all real numbers because it goes through every single number, all the negatives, all the positives. What about the range? Well, as we see right here, this is going up this way infinitely, this is going up this way, but it stops here at the x-axis. So our range is going to be y greater than or equal to 0, or the interval 0 to infinity. All right, so let's take a quick look at some graphs of functions. So here we've got some function x. We've got our x value. We've got our y value. Remember, f of x is the same thing as y. So we've got our y value, and here's the coordinate point, right? X and f of x, or y. So there's our graph. Which one of these are functions? Now, if you remember previously, I said no x can have different y's. So if we're looking at this first function, letter a, this x right here for 1, it's going to have a value of, for y, of 1 and a value of -1. That x has different y values. This is not a function. And what we can do is we can do something called the vertical line test. So if you were to go across your function and at any point you were to hit 2 points at the same time with a vertical line, you know that is not a function. So using that vertical line test as we go through here, we say that a is not a function. When we look at the vertical line test going across this function, we're not hitting any 2 points at the same time. So that looks like that might be a function. Same thing here. Oh wait, what does this mean? This means it's included here. 1 is included in this part of the line, but this open circle is saying that it's not included at 2, but it's then continuing on. So here, even though it looks like we might be hitting 2 points at the same time, we're actually not. And of course, on a circle, we are. So what's our conclusion? Which graphs are functions? That's right, B and C are our functions. These are our 8 basic parent function graphs. Different books call them different things, but this is essentially what they look like. We've got our linear equation, or the identity function. It's just a straight line. We've got our squaring function, or quadratic function. That's going to be a parabola. We have our cubic function, where you've got this little squiggle going in here. We've got a square root function, which we've seen a little bit of in this slideshow, where it's kind of starting here and going up and off in one direction infinitely. We have the absolute value function. That's always going to be a v. We have the rational function, or sometimes called the reciprocal function, where you have 2 parts to this function because you have some asymptotes here. But that's going to be your 1 over x. And then we have our 2 most common trigonometric functions that we use, our sine function and our cosine function. They both look very, very similar, but if you note, the sine function starts at the origin and then goes up and kind of does its squiggle there. And the cosine function starts at 1 and then does the same squiggle. So it's just offset a little bit by about half a pi is what it's set off about. Transformations. All right, so how do these functions move? How do they change as we add things to them? So we're going to look at this. So we have our parent function x squared. We have our child function, I guess you can say, where we're adding some value to the end of the equation. So let's see what happens when we add some number. So you can see the c here is changing. It's going up, and then it starts at the negative, and you can see that this is causing a vertical translation. So it's moving up and down when you add a number to the end of your function. A constant is added to the parent function. What about when we add a constant number inside the parent function? So we add it to the independent variable. All right, so now we've got our c value, where we still have our our quadratic function. We're adding c inside the function, and the c is going to be the value that we have over here in the box. So as this is rotating, or as this is going through, we can see that the parent function, or the function, is moving left and right. However, notice that when the c value is negative, it's on the positive side, and when it's positive, it's on the negative side. So it's a little opposite from what we would initially think. All right, so that's our horizontal transformation. What about reflections? All right, so the first one is if we multiply the parent function by a negative number. If we multiply that by a negative number, then we have a reflection across the x-axis. So here on the graphs, the blue is the parent function. We multiply by a negative, and you can see that it turns out down here. It reflects about the x-axis. What if we multiply the inside or the independent variable by a negative value? We have the opposite of the parent function. In that case, the reflection is across the y-axis. So here's our parent function, and our child function is reflected across the y-axis. What if we combine both of these things and we have the independent multiplied by a negative number, or it's the opposite, and we have the whole function multiplied by a negative? Then it's a reflection about the origin. So that means it's going to be a mirrored reflection right here at the origin. So you can see where this kind of goes up and that way. This is going to kind of come down and go off to infinity. So that's what happens when you have a negative in both places. So it's a reflection about the origin. All right. Our degrees of functions. So this is going to be based on the highest exponent in the entire function. So you're going to have either an odd or an even function. And a is the value that determines the direction of the function. Remember, a is always that coefficient that is right in front of your highest degree. So if a were a positive number greater than 0, we're going to see, and this is even, this is for an even function, we're going to see that it always the endpoints go up in the positive direction. If a is a negative value, the coefficient of the highest degree exponent, then we are going down in either direction. What about odd functions? Well, if a is positive, so maybe you had 5x cubed, you're going to have it going up to the right, and you're going to have it going down to the left. What if we had negative 5x cubed? Well, it's going to be just the opposite. We're going to be going up to the left and down to the right. And lastly, we have how do we do some of our operations and how do we work with our functions. So if we have these two functions, f of x and g of x, the first thing that we might want to do to them is add them together. You would see it in notation either like this, f of x plus g of x, or f plus g of x. And all you're doing with that is you're just adding each of those two functions together, basically dropping the parentheses, combining like terms. Nice and easy. We can subtract these two functions. Same type of thing. The only difference is make sure you distribute this negative sign across this second set of parentheses. And then you would simplify and combine like terms. We can multiply our two functions together. It would look like this, f of x times g of x, or f times g of x. Remember this, we've got this solid raised black dot. That's another way to write multiplication. So you're just multiplying these two together. Use FOIL, use the distributive method, whichever you like, but you multiply all of the parts in each parentheses to get your new function. And finally, we have the division function, where you're going to have it either as a fraction, or you could write it here with the kind of the slash, and you're going to have your function this way. Now remember, you cannot cancel this x and this x. It's got to be a factor of the entire numerator and the factor of the entire denominator in order to start canceling things out. And composite functions, everybody's favorite. Composite functions are when one function is embedded into another function. So that means we have g of x inside f of x, or we write FOG. Now notice this looks like multiplication, but it's not. This is an open circle. So what we're doing is we're going to put the g function inside for every x in our f function. So g goes inside f. So here we've got our 2x minus 3 for our f, but we want to put this inside our x for our f of x. So here we see where our x once was, it is now our g of x. So you would multiply that out, simplify, combine like terms, and you would have your new function f of g of x. Or you could go the other way, you could have g of f of x, where your f goes inside your g. So now your f function is going inside where your x is here. So we've got 2x minus 3 squared plus 1.